to the Hayden lecture hall. Before we begin, we would like to introduce you to the college, and we have our Queens College president here, Dr. Frank Wu.
Good afternoon. How is everyone? All right, are you excited to see some stuff blow up? I come every year for the show. Welcome to the beautiful campus of Queens College. I'll be very brief. So this chemistry demonstration is named for Chief College Laboratory Technician Thomas J. Hayden. That's who the room is named for as well. And it's put on by the Department of Chemistry and Biochemistry today. This is the 27th time that we've put on this annual show, so it is a long-standing tradition of this great institution. You know, science is just fascinating. It is so important to everything we do every single day, and chemistry in particular. I know that here at Queens College, our talented faculty and the lab technicians teach it in a way that it's meaningful, it's exciting, it will captivate you. This is just a tiny little bit of what goes on in the laboratories here at Queens College. We want you to have some sense of it. I'd like to commend and thank everyone involved for putting on this show. That includes, in particular, the Science and Education Division alumni who support the Finkenberg-Gaffney Scholarship in Chemistry. There are actually scholarships you can get to come here to study chemistry in particular. Do we have any Queens College alumni in the room? I know that at least one of the presenters is a Queens College graduate. So raise your hand if you're a Queens College alumnus. All right, thank you so much. So, I want to be sure to welcome all of you high school students. Our School of Math and Natural Science is the perfect place for you here in New York City, in the world's borough, to study chemistry or any other scientific field or math. It's a great place to earn your bachelor's degree or even to come on the accelerated track and earn a bachelor's and a master's in the amount of time that at most places, and the cost that at most places, will only get you a bachelor's. So think about that, and you get all sorts of hands-on experience here, and that includes so many other fields as well. I'll just mention a few. Astronomy, geology, nanotechnology, computer science, neuroscience, and biotech. There's just no limit to your options with a math or natural science degree here from Queens College. One of our recent graduates went on to an internship with NASA, and that showed that even the sky isn't a limit if you're here at this wonderful institution. I'm honored to welcome you, and I know that we're all here to see the stuff explode, so I'll stop talking, and it's just a great show, I promise you. We hope to see you when you graduate from high school right back here, and maybe someday you'll be one of the ones in front of the audience destroying things. All right? Thanks so much. Back to you.
So this is the 27th annual Hayden Show, and as President Wu mentioned, it was named after Professor Hayden, who has been doing demonstrations in front of his chemistry classes and camps and other events just like this since he started in 1955. As I mentioned before, the lecture hall that you're sitting in is named after Professor Hayden. And 27 years ago, the Hayden Show, where we get to see things explode, started with Dr. Streckes and Dr. Gaffney, and we continue it today in Dr. Hayden's honor. Here are just some of the names of all of the people who have put the show together. You're going to see many of them behind the lab bench, but there are many more in the stock room. So we're looking forward to a really great show. There are going to be times where you may want to have your phones out to take pictures and videos. There's a lot of cool experiments coming. So I'll hand over to presenters. Enjoy the show.
Okay, so there we go. All right, do we have any birthdays in the house today? No? Anyone's birthday like recently or maybe coming up? Tomorrow. Oh, tomorrow. make sure you make your wish. Oh, I don't know, Billy. It looks like your wish might not come true this year. Today. Everyone cross their fingers for Billy. I guess it didn't work.
So, can they get the birthday cake?
Carbon dioxide, good, right? So, it would be reasonable if we would say like dry ice would put out a fire, right? Yeah, that makes sense. And next month we have Valentine's Day showing up, so I'm going to show you one of the greatest loves of all time, the love between magnesium and oxygen. So, for magnesium and oxygen, their burning love can't even be put out by the fire extinguishing properties of carbon dioxide. So let's see. Lights. Burning love, I call it. Thank you very much.
You know what is that? Maybe I need a mic. Alright, so here I'm here to make some cool drinks for you. Usually water is very nice, so this is some nice water. Cool. Maybe something very interesting for you guys would be to have a nice colored drink, right? So when you see some color, see, ooh. Let's see if we can get some color. Here we go. And let's make it for everyone. At least everyone can get a drop. I guess there's a big audience here. But if you want to get back to water again, we have again chemicals for that too. We can make the water and make the color disappear just like that. Magical. The whole thing is gone. Maybe you want something nice, cool, healthy. Healthy, what do you want? Milky. I have milk for you. But skim milk. No lactose. There you go. My skim milk. So let's just make it for all. Skim milk for everyone. Maybe I think I used like one thing. I had no milk. Maybe something like chocolate milk. I have chocolate milk for you. chocolate milk. I would rather have water back. Yeah, you want water? Okay, I'll make water for you. This is water for you. Right, there is his chocolate milk turning into water. Don't drink it! Not even drinking it. Alright, the whole thing is made into water. I can just pour it a few times, everything becomes water. Clean water. Now it is chemically purified. Right, this is called the soda series. You want to know the chemistry behind this? There is a paper in front of you. You can read that. That tells you how the chemistry works. Thank you.
All over the place, we have these things called dirigibles. You know what a dirigible is? It's a blimp. Fancy name for a blimp. You know what was in a dirigible? Hydrogen. They put hydrogen in a dirigible. And there was this thing called the Hindenburg, and it was in New Jersey. And it was flying over New Jersey when suddenly, for whatever reason, unbeknownst to anyone aboard, it caught on fire. And it crashed, but it was filled with hydrogen. If you want to go on that go on, right? Is your insurance paid up? Insurance. Health insurance, life insurance. Can you come to this one? You saw the last explosion? No. I'll do it, it's okay.
What if it has something?
Ladies and gentlemen, what you just witnessed was the difference between hydrogen and helium. Both gases less dense than air, but hydrogen, extremely flammable. Helium, not so much. Thank you very much.
Alright, I'm back. So here I'm going to do something, the same hydrogen gas, but I got it trapped in a bottle here. So I want to see if these bubbles are going to be as explosive as his balloon is. Maybe? What do you think?
They're just little tiny bubbles, though.
They're tiny bubbles?
Yeah.
Not be as good? Okay. She's right. She knows more chemistry than me anyway. So I'm going to put those bubbles in here. Okay. Let's see if these bubbles are any good.
Now my mom's
That one doesn't like. Yeah. That's exciting. Okay, so here is something else. This one is called as the stoichiometric mixture, the right ratio, the mixture of the hydrogen and the oxygen put together. Does anybody know what's the ratio between H2 and the O2 in water? 2:1, okay. 2:1 ratio, we already pre-mixed it, but it is in the form of a gas. It's going to try to form water when I'm lying down. So let us see whether it will fully combine or whether it's going to combine with any effect. Somebody is looking for a thunder, I guess. Let's see if it has got an explosion like thunder. This one is crazy. These matches are no good.
In it, and the oxygen in a liquid form. And this is Sally, and this is Pete, and Pete and Sally go out, and Pete gets in the way of the hole for Sally because he doesn't want Sally to fall in the hole, and Pete falls in the hole. Say goodbye to Pete. This is the combustion of all the sugar inside a gummy bear. And it's just reacting with the oxygen that's inside the test tube. And it's quite interesting. And when all the sugar's gone, the reaction will stop. But does that mean all the oxygen's gone? No. Well, that's a good answer. Because we'll just throw Sally in for good measure. Wait for it. Wait for it. Uh-oh. There we go. And that is what we call the gummy bear sacrifice. Thank you very much. I lost my wallet. I need some money. Does anybody have any money? You have somebody? How much you got? You got 20? No, I need more than a 20. What do you got? 30. I need more than 30. I need a big bill. Who's got a big bill? You got 100? Let me see it. Hook me up.
I think you dropped it. I think I found it down.
Oh, look at that. Oh, look at that. Team dropped your 100. Oh. How do I know this is yours?
Because you don't really find it.
It's yours.
Yeah.
Right. It's definitely 100. What am I doing? Well, it's not my money. I don't care about the money. I want to put it in some really good stuff. We call it alcohol. Stuck it together. Let's get it back in there one more time. Really hold it down there really good. Yeah, there we go. That's good. Thank you, Dr. Galapalo.
Money.
So money is a very interesting thing we have in the United States, especially our money, because we call it paper money, but it's not really paper, it's really cotton linen. And the linen, actually, the cotton has a very unique property where it absorbs certain liquids. And I had a small mixture here. It was alcohol, but it also had water in it. The cotton fibers actually absorbed the water before the alcohol, even though they're mixed together. And the alcohol stays on the outside. Meanwhile, the water absorbed into the cotton fibers, protected the money, and kept it brand new for me to take. Thank you, Dr. Galapalo. Have a great day. I know you weren't.
You guys having fun yet? Yeah! We're gonna get to some other tiny science, which is showing you different types of solution B, I started backwards, but it's okay, mixed with another solution A. And when we mix them together, they're supposed to react, but this reaction takes a little bit of time, so you're going to help me out. Let's start counting. 0, 1, 2, 3, 4, 5, 6, 7, 8. Oh! That is great. Now we're going to have another one. This one is a little bit different, because in this reaction, we form something that we call an intermediate. An intermediate is a product that you get before you actually get the real product. So we're going to mix 3 different solutions. Solution A, we have solution B, and we have solution C. And when we mix them in specific orders, they produce a product that is not the final product, but then, in a glimpse of a second, produces the third. So keep watching, and if we can have the lights off. Now the next thing we'll do, you can turn the lights on for now. The next thing we can do is study the science of a firefly. What's a firefly, guys? It's a fly with some light, right? Have you ever seen a firefly at night? Yeah. What happens? It glows, right? So that glow is an actual chemical. It's a chemical that we have right here, and we're going to make that magic in a bottle. So when we mix that, and if I can have the lights off, please. Yeah, the firefly in a bottle. Thank you guys, enjoy the show.
Such as calcium chloride, lithium chloride, barium chloride, strontium chloride, follow the mountain ball, cupric chloride, yes, there we go, we're learning. Chemistry is definitely contagious. Sodium chloride, yep, there we go, sodium chloride, and boric, no, boric acid, you got that one wrong. And so those are these wonderful salts that we have. And then what we do when we have fireworks is we give it some type of activation energy to make the electron go to a higher, well, energy state. Goes up in an electron shell, and it becomes what we call the excited electron. But we still don't see color yet. We only see color from that electron that is in that excited state when it wants to come back out of the excited state. So the first thing we do when we make fireworks is we have to excite that electron through different colored salts. And so we will now excite the salts. Give it some seconds. We gotta make those colors come out. We couldn't. Turn on the lights, they quick. incredible.
Now do they remember which ones are which?
That's a good question. I don't think I remember. Oh wait, lithium, strontium, barium, potassium, cupric, sodium, and boric acid. Alright. Yeah, boric acid's nice, I like it. You know, gives me an idea. We should make fireworks right here in Remsen Hall. Does it have Yeah, right? Oh, what a great idea. I'm glad you thought of it. And the very first thing we need to do is we need to take that same chemical that I poured into that liquid and make what I like to call a propellant out of it. So if we can make the cap come off of this through a small spark, I guess we can't do it.
There you go. I can give you the fuel.
Give me fuel.
Yeah.
1 drop, he says. I've been taught well. 1 drop.
That's what you need.
1 drop. Nope, not working. Oh, it does work. Oh, so now we take the big bottle.
Can you see the colors now? It's coming up so nicely.
It is nice.
For 1 second, turn it off. Alright, you guys can see the color now much better. Those who cannot see, stand up and see right now. One more time before you put them out. Oh, the intense. There are 2 red colors. Crimson red and orange.
Those are pretty. Your job is to see what color I put in here. Can you do it? Yeah. You sure? I don't know. I don't even know whether it's going to work or not. 3, 2, 1. I tried. Maybe later. Color fireworks. Thank you very much, everybody.
Okay, guys. How many of you here have heard of acids and bases? Anybody? Yes. Do you have any acids and bases at home? Okay, great. So, how do we know if something's an acid or a base? How do we know? Okay, good guess, pH meter. We don't want to test it ever though, right? Right? We know acids are sour and bases are bitter, but we have a unique method called the universal method to determine whether something's an acid or a base. Alright? So I have here some water, and my partner's going to pour some ammonia in it. What is ammonia? Acid, base? Anybody?
It's a base.
Okay, go ahead and pour it in. So I'm going to go ahead and add my universal indicator. And does anybody know what color this is going to change? Purple. Purple? I heard purple. Purple is a good choice. Turns a nice purple color. Alright, so that means bases are purple, right? Ammonia is the base. So what happens if I add this stuff? What's this called? Dry ice. Anybody know it's an acid or a base? Acid. Dry ice, CO2, right? So it's neither an acid nor a base, but when we put it in water, it forms carbonic acid, which is an acid. So you can see it's going through, it's neutralizing the ammonia. It's turning blue, right, for neutral, then it turns to green. And if we keep adding it, we'll continue to see a color to acidic. Okay, so we started out purple. And anybody know what HCl is? Is it an acid or a base? Let's find out. Let's find out. Let's add some HCl. Ooh. So we got a different color here. This is red, so this is acidic. HCl is a very strong acid. Can we turn it back, do you think? I got some ammonia here. What color color would he turn back? Purple? Let's see. Woo! Green. There goes green. Almost. Green. You want to stay on green? He doesn't want to change. Let's see. Get it back. We're getting there. Yay! I think we're there. Yeah, you can see the purple, right, guys? Yay! Turned it right back. Okay, there you go, guys. Universal indicator. Thank you.
Hello, I'm back again. Banana. Flowers. Oh, so pretty flowers. Pretty flowers. Keeping coldness. I love it. I love me some cold. What I have here is called a doer. And this is filled with something called liquid nitrogen. Bouncy. Banana. Yup, definitely a banana. Balloon. What's in the balloon? Yeah, I'm filled with helium. What's in the balloon? What do we breathe? From where? Oh, air. Yes, air is in there. Yes, I agree. You don't have any helium? No. That's why I'm so round to the ground. So, do we have the other doer? Got the other doer? Yep. This is a bigger doer. I love it. And this is filled with liquid nitrogen. Very, very cold. Very cold. And so I'm going to pour the liquid nitrogen on the balloon. And what's happening to the balloon? What's happening to the air inside of it? Ooh. Ah. I'm melting! I'll get you, my pretty! Oh, that's cool. I can pack this up. Yeah, look at that. That's nice. I like it. It's a balloon. It's fluid. Look at this. It's fine. It's fine. I can do magic. Watch. Grow larger. Get bigger. It's a balloon! Huh? Does that mean this is still a banana? So this is a cryogenic effect of liquid nitrogen. It makes things really, really cold. The balloon, it took all the air molecules and put them together and shrunk it. But for this, it doesn't bounce anymore. For the banana, there it is. There it goes. Up there it is. It's swimming. For the banana, it's so hard. I can take the banana and make a hammer out of it. And for flowers, I can dip my flowers into my liquid nitrogen, and I can freeze them, and I can take them out, and they'll still be flowers. Yay! But they'll be very crispy. There you go. Liquid nitrogen, ladies and gentlemen.
Superconductors are basically certain types of special materials that when you cool it down using what you just used right now, liquid nitrogen, to about -200°C, have unique properties which allow them to expel all the magnetic fields inside them. And that sounds a little technical, so I'm just going to show you what that actually means when you actually expel all those magnetic fields in what's known as the Meissner effect. You get something like this. There you go. A little bit of a levitation going on. Now you see, what's happening here is that when it's super, super cold, it creates this magnetic field that expels outward and creates this force keeping it upward. And this specifically is a type 2 superconductor, which means it lets little holes punch the magnetic field go right through it. What's really interesting is what happens when I put it on top of this. Because what I can do is, if I can see it against the screen, I can spin it around. I can spin it around super quickly. Get it? There you go.
Yeah.
And most of you are thinking, well, I've seen magnets before, right? I know how magnets work, right? That's not pretty cool, right? What about this? If I turn it upside down, I get the same sort of effect, and that's not something a magnet can do. So if I turn it upside down, you can see that it's actually floating in midair. And this is actually something that isn't just science fiction, that we just use it in a laboratory and it just moves it all. We use this in things called maglevs, which are magnetic levitation trains. They exist currently in places like Japan, China, and Korea, where they're used to move trains at speeds of up to 370 miles per hour, which is more than 2 to 3 times faster than what our normal trains go. So if you're ever wondering why isn't the MTA moving as fast as what they do in those Chinese and Japanese countries, because we haven't actually created these magnetic levitation trains yet. There are some at work right now in the Northeast, from New York to Philadelphia, and one from Las Vegas to California. But you know what they say, when something's at work with the government, it's never really finished until someone's got his paycheck. Anyways, that's magnetic levitation, guys.
Are you having fun yet? Yeah! You like fire? Yeah! Of course you do. You should come to Queens College. You should be a chemistry major at Queens College, and I was. I got my master's degree here, and then I became a teacher, because I like to, well, make fire. Anyway, this is thermite. This is thermite. Thermite is composed of iron and aluminum. And when it's mixed together, who's seen, oh look, Thomas. Who has seen Mythbusters, and they cut the car in half with thermite? You've seen that? Oh, one person in the back. It's pretty cool, isn't it? Thermite's really neat. They even use it in space. NASA likes to use it for rockets. It has some drawbacks. When you ignite the thermite, you can't stop it. And if you make a mistake with the thermite, which has been known to happen before, sometimes, just sometimes, you burn holes through things. Thermite burns at over 3,000 degrees. It is a one-way reaction. Once it starts, you can't stop it. And we're going to witness the thermite right in front of us, right here. And what we're going to see is I'm going to light this fuse with this torch. And when I do that, it's going to burn down and it's going to ignite the thermite. The thermite's going to take a second, but once it starts, you can see the thermite drop and drip right down through the middle. Are you ready? That's the fuse. That's the thermite. This is old thermite bonded with new thermite. This is new thermite. And then there's a piece in here still, an ingot. And if I do it just right, I can fuse it to my tongs. Ladies and gentlemen, thermite. Thank you very much.
Only my kids feel strong today. Alright, so I am going to cheat a little. I'm going to use chemistry to light it though. I mean to crush it. So what I have in here right now is rubbing alcohol. I put it in there as a liquid. Why do you think I'm shaking it? Who said that? To get it all around, but someone said, make it into a gas. Good, right? I guess I really do need to start going to the gym. Not as jacked as I thought.
Okay.
All right.
All right.
Everyone hear me? Yeah. All right, I got a quick question for you guys. What kind of food do elephants eat? What do I got? Plants, right? But not all elephants, right? Some elephants, I know an elephant over in the Bronx Zoo, Sally. She loves candy. Problem with candy, guys? What happens when you eat too much candy? You get cavities, right? So we gotta make sure that she has her own toothpaste. But elephants got big teeth and even bigger tusks. How are we gonna make that much toothpaste? Well, I'm gonna tell you. One of the main ingredients in some toothpaste is hydrogen peroxide right here. So we're gonna add a little bit of hydrogen peroxide into this mixture, right? And then, what's toothpaste without the stripes, right? What colors do you guys like? I got it. Which one do you want? What, red, blue, you got? Alright, got blue here, we're gonna add both. You know what? Let's go crazy, right? Let's add both. We got blue, we got red here, let's add a purple, you know? What the hell? Alright? And now, we're gonna add a little squeeze of this detergent. And, oh, that's kind of legit, right? But you know what? This reaction is just going very, very slowly. But what I can do is I can catalyze it to go even faster using this, potassium iodide. So if I add a little bit of potassium iodide, what happens is... Alright. Now look at all these things all on the teeth.
Love setting stuff on fire. So when we go in the lab, we have these little things where gas would normally come out, and you can turn it, but nothing comes out. Probably because they don't trust students with fire, but at my school, they probably also don't trust me with fire because I would do some crazy stuff like this. So what I have in this, there we go. Alright, so what I have in this bucket here is just soap and Dawn dish soap. And coming out of this hose is the flammable gas that you guys saw make fire with the Bunsen burner here. So these bubbles here are chock full of nice flammable gas. And I want to make a lot of bubbles for what I'm about to do. Alright, so this is probably why they don't trust us with fire at my school. I take the cell phones away because students have a hard time concentrating. And I thought that it was just like I was taking social media away from kids so they can't like text or whatever. But I found out recently that I'm also taking students' mirrors away from them. The other day I saw a student actually using their calculator as a mirror during class because they didn't have their cell phone to use. So what I'm going to do right now is I'm going to use chemistry to make a mirror. being a little too rough with it. Alright.
You can do it slowly.
So let's see if I can make a mirror for my student
Takes
who
about a minute's time.
apparently the lip gloss was very important. We were supposed to be doing math, but she was using her calculator as a mirror instead.
It is for someone who wants to say now it's for tomorrow. Can you see your face here? Right? That's how your mirrors at your home is made of. They actually put a... Oh, you're getting there.
Oh yeah, I can see myself. I can put lip gloss on now.
It just takes a minute to make a mirror.
It only takes a minute and some chemistry, which is why you should pay attention in chemistry class. And never put on lip gloss in the lab. Alright, so can you guys see yourself in it?
There you go, guys. That's mirror making.
I'm gonna grab my umbrella just in case things get crazy. Alright. So, there we go. Alright. Step back, things are gonna get wet and sticky in here. You guys ready? Count me down. 3, 2, 1.
And what I have here is what we like to call a carbide cannon. What comes out of cannons? I'm going to give you my socks today. I took them off just for you. But what's really interesting about the carbide cannon, it has something in it called calcium carbide. Calcium carbide, when it reacts with water, it creates acetylene gas. And acetylene can be a lot of fun. Even the coal miners used calcium carbide in their old school lamps. They used to wear them on their head. And then that went to something called vaudeville, where they put those lamps on front of the stage and they coined the phrase, "in the limelight." The problem with the calcium carbide is, in a coal mine, is sometimes it builds up a little bit of pressure. And when it builds up a little bit of pressure inside that coal mine, crazy things like to happen. Alright, here we go. Water, cannon, calcium carbide, mix, aim, wait there, fire. You like that, don't you? Do it again. No socks. Okay. I like the big bang. Mixture. Match. 3, 2, 2.5, 2 3/4. 3.
Everyone, yes, please pass the Simon's dirty socks back. I'm sure
Yeah, give my
he
socks
wants
back.
them and you don't. Thank you.